Thank you for coming back. Let's start the last session today. The first speaker is Miquel Huix-Rotllant, and he's going to present unlabeling the photochemical mechanism of ion tris-2 bipyridine by a wavepacket dynamics. Please welcome Miquel.
Thank you. So thanks a lot, and thank you, Mike and Chill, especially for inviting me for this opportunity of coming back to Korea that I always love. It's the third time I visit Korea, and I told you the first time it was the first time in Asia. It still is the first time in Asia. It's always in Korea. So the first, the second, and the third. So I really enjoy, and I always learn new things about this country. It's fascinating. So, okay, today I decided to speak about photochemistry of iron complexes, in particular this iron tris-bipyridine, which is a nice example of a molecule that everybody thinks they know very well, but it's a good example also of the devil is in the details. So yes, I'm going to speak about photochemistry with just a small recall of iron complexes or these generic spin crossover reactions. So they can be light induced, but they can be induced by other external stimuli like temperature, like pressure, all sorts of distortions can make this kind of molecules or materials go from a low spin configuration to a higher spin. So in the case of iron, the lowest spin is going to be a singlet, the high spin is going to be a quintet. And the main question is how to go from one to the other via the excited states. So this is called the forward or the light-induced spin crossover reaction. Is called also light-induced excited state trapping reaction. So it usually takes less than 1 picosecond. Even it can take less than 500 femtoseconds. It's really fast, which is kind of a strange thing for iron, which is not very strong. It's not having very strong relativistic effects. And the quantum yield is almost 1. And then you have the reversed light-induced spin crossover, which takes a bit longer, and the efficiency is much less. We studied this reaction recently for a similar iron complex. I'm not going to speak about this today. I'm going to speak about the forward reaction. So, well, the main thing to know about iron is going to have these d orbitals, which in octahedral field, they are going to split into two groups, the T2G, which are the dx, dy, dz represented here. And the vacant ones at the lowest spin, they are going to be the EG, is the dx square minus y squared, and the dz square. These two get destabilized because they are through bonds and they make a sigma star interaction with nitrogen. That's why they get into the virtual space. The other three are in between the bonds and they get a bit stabilized. And so when we go to the highest spin, we are expanding this complex. So the EG orbitals go a bit down, and then we get this quintet open shell that is being formed. So it's actually 3 states because this beta electron can jump on the other 2, and we still have the same state. So when you put when you surround iron this D in this octahedral field, and you have a chromophore around, so as in the case of bipyridine, you also have these pi and pi star states that enter in the game. So depending on the oxidation level of the metal, so you can have either MLCT or LMCT. So MLCT is a transfer from the occupied T2G d orbitals of the iron to the pi star. And if you, for example, remove 1 electron because you go from iron 2 to iron 3, then you can get LMCT, which are lower in energy. So the MLCT are much higher and are not playing part of the game. And this is very interesting because then they can play with the oxidation state. And this is very important in, for example, photocatalysis to stabilize LMCT states and MLCT states long enough to get this photocatalytic activity. This complicates a lot the electronic structure. So here I show the band structure of iron tris-bipyridine. So this is the lowest spin state. This is the singlet A1. So we excite more or less in this area here, in this MLCT, which is actually forming a band of singlet and triplet states. There are many states in here. And then with less than, let's say, 200 femtoseconds, we go down and we get into this highest spin quintet state that is shown in red. So the main question is how we go from the MLCT singlet to the high spin state in such a short time. So, of course, you can always rely on experimental results to time-resolved experimental results to solve you this issue, but actually they complicated it much more than solving anything. So I just will make a summary of the so many experiments that have been performed on this system. So one of the first, at least to my knowledge, is in 1992. So this is time resolved UV visible. So they used actually a very long pulse delay between the palm and the probe. So they just couldn't see anything. So it was just the initial state, which is the singlet MLCT, to the final high spin state in less than 700 femtoseconds. So in 2007, we got time result fluorescence results. So they determined, they saw a signal, a very clear signal of the singlet MLCT to the triplet MLCT. So this was one of the first times in which these triplet MLCTs were shown to be important intermediates. And this is this signal here. So it's very clear signal of triplet MLCT. And then they said that they had another signal of transfer of triplet MLCT to triplet MC with 120 femtoseconds, and from the triplet MC state, so metal MC is metal center. I think I didn't say that. So it's a DD triplet. So to the highest spin, it was about 1 picosecond. So with the development of these X-ray electron lasers and these new very fancy types of lasers, so we got new knowledge and new mechanisms on this system. So in 2014, there was a time-resolved X-ray emission. So this is this very nice spectrum here. So they said that we have very similar to the 2007, so a transfer from the singlet triplet MLCT, because they couldn't distinguish the two, to the triplet MC, on the triplet T1, and from the in 150 femtoseconds, and from the triplet T1 to the highest spin in 70 femtoseconds. So actually, this was a bit disappointing, because actually this signal of the triplet MC states is almost confused with the noise. So with this area in here, I still try to see where the signal of the triplet MC state is, but I have a hard time to see it. So it's you need to have a lot of imagination to see this triplet MC states, which is confused with the noise almost. So in 2015, there was another time-resolved UV visible, much more fancy than the one in 1992. So the pulses were less than 40 femtoseconds. So they could see a signal of MCs very clear. So again, it could not be distinguished whether it was a singlet or triplet MLCT, but they saw something that has never been observed and never again observed with any other experiments. A very fast transfer to the high spin state in 55 femtoseconds. With time resolve Xanes, they saw exactly the same, but they said that this 55 femtoseconds is not possible, so it's 120 femtoseconds. And finally, the last one is in the same year as time resolve Xanes is XUV, so photo emission. These guys, they said, okay, we observe 1 MLCT to the 3 MLCT that takes 16 femtoseconds, like the time-resolved fluorescence. But then they said that 2 mechanisms are possible, one going from the triplet MLCT to the triplet MC, and then to the highest spin in 70 femtoseconds, and then a triplet MLCT to the highest spin in 36 femtoseconds. But from all the spectra, I have to say that this one is, for me, impossible to understand where they see these signals. And actually, all these X-ray spectroscopy rely on fitting of these populations that sometimes are very difficult to observe. So it is right now a bit confusing what is the exact mechanism, and that's why we tackled this problem, and we used wavepacket dynamics to try to understand what is the excited state mechanism. Just parentheses, because it's a nice development we did with Dehum, with Chol, and with Bujin, that I don't know if he's here. No. Anyway, so also with Bujin. So we did a method to extract X-ray spectroscopy based on MRSF, and I do this parenthesis because my initial plan was to apply to these iron complexes and to reproduce these complex spectra. Well, it's a bit difficult, but maybe we will reach this level of of complexity in the near future. But in the meantime, I just wanted to show that we developed this strategy of using MRSF with MOM to extract X-ray spectroscopy. Just to be very brief, so in MRSF, it's a spin flip method. So we start from a valence triplet reference, so the lowest triplet state, from which we apply this one particle, one hole spin flip excitation operators, and we extract the valence states. That's very common. So we get errors which are similar to the TDDFT ones when we don't have double excitations. When there are double excitations is much better, and when we have a strong correlation, so meaning that the ground state is multi-configuration, it is no doubt that is superior. However, for the core excitations, if we apply the core balance separation, we get very similar to the TDDFT with errors that are around 20 EVs, which is pretty high. But what we did is just to apply the what is done in delta SCF, so MOM. So if you start with a guess in which you have already a hole in the 1s, and then you apply a kind of restriction in the SCF, so that, for example, your orbital rotations are the gradient of the orbital rotations are decreased at the beginning of the SCF. You can end your SCF in a local minimum that is actually an excited state, and in which is very close to your initial guess. So in this case, we get the orbitals that have already a 1s core, and so we built in the orbital relaxation of the X-ray process of extracting 1s electron already in the SCF. So then we can apply the spin fleet in the same way. So that's the standard MRSF, and so we get our core states now within an error of less than 1 EP, which is pretty amazing. I think we didn't expect that it was so good. And also we can extract some of the so by doing a valence excitation, some of the time resolved X-ray spectrum. So time resolved meaning that we excite one S electron, and then we excite 1 pi star transitions. So, for example, we showed that for the case of the time resolved X-ray spectrum of timing. So that was a really nice result. So here is a signal that is appearing in the time resolved X-ray spectrum of the N-pi star, and here in white is the experiment. So I think we can say that we are in less than 1 EV even for the time resolved X-ray experiment. So going back to the iron tris-bipyridine, so these are the two mechanisms that are proposed. So the first one would be from the singlet MLCT to the triplet MLCT, and then to the highest spin. And then the indirect mechanism, which will be a singlet to triplet MLCT in the same way as before, but going to the triplet T1, which is a metal-centered triplet, before going to the high spin state. So what is the leading mechanism? So we are trying to resolve this question. And another one is how much time does it take? So the singlet to triplet MLCT, in principle, by experimental results, is 15 to 16 femtoseconds. And then the triplet MLCT to the highest spin, by an intermediate or not, it takes either 55 femtoseconds to 150 femtoseconds. So what we used is to do the quantum dynamics on singlet, triplet, and quintet, considering the singlet and triplet MLCT bands, the triplet MCs, and the high spin state. So we need to treat all the non-adiabatic couplings between this state, and also we need to treat the spin orbit couplings. So we found that the best way to do that was by using this multi-configuration time-dependent Hartree, so quantum wave packet dynamics. So here is a bit the answers we are using to propagate our time-dependent Schrödinger equation. So for each of, let's say, we have a Hartree product for each of the vibrational dimensions that depends on time, mixed with these coefficients that also depend on time. So this is our answers for the wave packet, and then we expand the single particle wave functions in terms of a primitive basis in which only the coefficients depends on time. This is very similar to the LCAO procedure in which we would have like molecular orbitals and the atomic basis. So it's the same for the wave packet. Then we can write a very nice equation of motions, one for the coefficients and one for the single particle basis. With the constraint that our total potential can be expressed as a product of single particle functions, and that is a bit what complicates the application of MCTDH, because directly what comes from electronic structure is not in that form. So we need to apply a procedure to map the electronic structure into a Hamiltonian that satisfies this condition. Anyway, this is a bit the procedure that we do. So we select a vibrational space. Usually with such big molecules, we cannot select the whole vibrational space. We just take a number of normal modes that will represent more efficiently our photochemistry. Then we compute the potential energy surfaces along all these modes. Then we map this information, these surfaces, into a diabatic Hamiltonian that is in this a nice product form, and then we apply our wave packet dynamics. So this is a bit the model that we need to construct for this iron tris bipyridine. So in the diagonal we have the low spin state, the two important MC states, triplets, the triplet MLCT band, the singlet MLCT band, and the higher spin. So in the diagonal, we have our diabatic energies plus a potential that depends on the vibration, on the normal mode that we selected, and this we expand in terms of a Taylor expansion in the coordinates up to fifth order in this case. Then we add the non-adiabatic couplings in the blocks between triplets and between singlets in this case. So the non-adiabatic couplings in our case are just diagonal with respect to the vibrations, and then we add the spin orbit coupling that we only compute at the reference geometry, which is the minimum of the lowest spin state. So this is a bit the coordinate space that we are using. So the reaction coordinate is the expansion of the complex. So this is a symmetric expansion of the three bipyridine units. Then we have two Young-Taylor distortions, which are important for representing the minima of the MC states. So these states here. So these correspond to the compression in the equatorial and decompression in the axial. So compression in the axial and decompression in equatorial, or decompression in axial and compression in the equatorial. So this is the potential energy surface represented here. So we have this typical double well that appear in the Young-Taylor distortions, and then we add yet 6 ligand modes, which corresponds essentially to several combinations of the CC stretching in the bridge between two pyridine units, and this is important to represent the displacement of the potential energy surface to represent the minima of the MLCT states. So with that, this is the main result after doing all this procedure. So these are the plot of the diabatic populations of each of these states in time. So we start from the bright MLCT singlets. So we have a very rapid decay of these states. And then this is concomitant to the buildup of the triplet MLCT, which is this green, and also a buildup of the triplet MC. That was a bit the confusion of the experimentalists, that these two were building up and they didn't know which was the intermediate. Well, it's difficult to say which is the intermediate because we are having both that are built up also in here. And then after some time, we have a buildup of the final state, which is this pink one, which is the highest spin state. So at least, well, we are more or less hoping that these dynamics are correct, but still we are not, we are unsure of what is the potential kinetic model that represent this evolution. So we could have actually from the singlet MLCT a transfer to all these triplets, the triplet MC, which is higher in energy, a triplet MC that is lower in energy, or the triplet MLCT. Experimentally, they cannot determine whether it's coming actually from the triplet MLCT or the triplet T2 or T1. So we need to consider the three, and then all of them can be transferred between them and to the highest spin state. So this is a bit confusing, and of course we can start deriving kinetic models to see which one gives the best fitting of the surfaces. But another thing that we can do is to deactivate couplings in our model Hamiltonian to see whether there are transfers which are possible and transfers which are not possible within this scheme. So we did that, and I just showed two of the reduced dynamics. So these are dynamics in which we deactivated couplings. So in the left, we have the deactivation of the triplet MLCT to the high spin couplings, meaning that we force that the transfer to the high spin state comes from the metal-centered states. And we see actually that we built up the highest spin state in a pretty much a similar way as before. Whereas on the right, we deactivate all the triplet MC couplings to the higher spin, and we see no transfer, meaning that we can neglect the mechanisms of transfer from triplet MLCT to the higher spin. So in fact, what the experimentalist said, that we have a transfer between these two, is actually not appearing. And we fit it within the using this model, and we see a very nice fitting of our MCTDH dynamics. And actually, we can say that the fastest mechanism is a transfer from one MLCT to a triplet MLCT, as the experimental is determined. But then we have a very fast transfer to the lowest MC state, and finally to the highest spin state. So for the first transfer, we are a bit longer in time. So instead of being 15 femtoseconds, it's 55 femtoseconds. But this we attribute by the fact that we reduced the number of vibrations that relax this manifold and introduce non-adiabatic couplings that we are missing in our vibrational space. But then for the 3 MLCT to the highest spin, we are via this triplet MC state, we are getting quite on the times X the experimental is resolved. So that is what I wanted to say. So thank you for your attention.
Thank you, Miguel. Now we are open for questions.
Very nice to